All right, welcome to 1.7 Periodic Trends for AP Chemistry. This is going to explain the relationship between trends and the periodic table with atomic properties of elements. Now, one thing you have to remember is that writing the electron configurations that are exceptions to the Abafu principle will not be assessed. So there are certain elements based on their atomic size or electronegativity or ionization energy that their electron configurations, the shells fill up differently. Those are not going to be assessed. You will have electron configurations on the AP test, but not those quirky ones that are kind of out of order. Okay. Now, the first way that the periodic table is broken up is by atomic number. So it goes not necessarily by atomic mass, but the atomic number does increase from left to right. Why do I mention that about mass? Well, look at argon. Argon is 39.95 AMU. So potassium, being the very next element, should be heavier, but it isn't. It's slightly lighter. So you can't, in general, the masses do increase as you go across from left to right and down, but the one that definitely does increase from left to right, top to bottom, is the atomic number. And the atomic number tells you the number of protons. The other way that it is broken down is by subgroups or the subshells, the S block, D block, Pli, and F. Here's two different periodic tables to show that. Now, most, if not all, trends can be explained by the arrangement of how the electrons fill up the shells based on Hund's and Abafu's principle, and applying Coulomb's law. So let's get into the trends. So let me flip this over. So the first trend we're going to be talking about is Coulomb. These are like key terms. Coulombic attraction, electrostatic interactions. This increases with charge, and it increases with a decrease in distance between particles. This Coulomb's law really talks about how the attraction between two charged particles is proportional to the magnitude of the charge. But inversely proportional to the distance between them. Okay. There is what's called effective nuclear charge and electron shielding. We don't have to worry too much about electron shielding in this unit, but you need to be aware of the effective nuclear charge is Z with the EFF. And then shell model. Okay. Now, the first trend we're going to look at is ionization energy. In general, there's first ionization energy, there's second ionization, third ionization, and even fourth. Now, when we get into the periodic trends, we did cover this in general chemistry, honors and regular. But it's not just about the arrows. So I kind of want you to stray away from just relying on the arrows. There's more to it than that, right? But what ionization energy does tell us is that from left to right, starting over here to right, ionization will increase, which means it takes more and more energy to strip off electrons, and it increases from bottom to top. So first ionization decreases as you move down, and then first ionization energy increases as you move across. Okay. Now the arrows are pointing to where ionization or the trend increases. This is talking about, because we normally read left to right, top to bottom. Okay. So left to right, it increases, top to bottom, it decreases. Right. Here's another way of looking at ionization energy. It's the energy that it takes to strip the electron. So as we go across, it shoots up, then we go down to the next period, and then it kind of staggers and then shoots up. So each one of these like positive linear lines that are kind of up, down, but in general, it goes a positive linear, is a different period. So here's period 1, 2, and then 3, and then it started 4. Okay. Now, the inner shells, shielding, this is basically what shielding is. Inner shells of electrons shield or block the proton's force of attraction. So when you've got a lot of shells, let's say 5 shells, these inner electrons in shells 1 and 2, those are so close to the nucleus that they're kind of blocking that magnet pull that the positive protons have on the outer electrons. That's why the atomic radius increases as you add shells, but also slightly increases because the protons, even though there's a lot down here, you've got these inner electrons shielding and blocking that attraction. That's essentially what a shielding is. Okay? Now, from the previous page, it talked about there's a few places where the ionization energy does not appear to follow a trend, where it kind of goes up then down, and maybe jags across and is even. Those are those unique elements. So we got beryllium and boron is an exception, okay? And this is what I'm talking about. These are the things that are not going to be assessed, where you go S2P3 to S2P4, okay? You're not being tested on those, but it talks about how the ionization energy does not seem to follow a trend. Here it looks like it doubled, but this looks like it quintupled almost. This is 1400, this is 7700. That's more than doubled, okay? So it just shows, and then here, about 3,000 more, 3,000 more. This is 5,000, then it goes 3,000, about 4,000, and then almost 7,000 here. So there are those unique situations. So why does, as we go up in number, does the ionization energy jump so much? Well, that's because you're removing more and more electrons. So the less electrons there are, the more powerful those protons can pull on those electrons. And that's really what ionization energy is. By examining the successive ionization energies, we can determine how many valence electrons there are. And then once they're removed, you see that large jump. Okay, so there's less shielding from the inner electrons, and those protons have more positive to pull, so you get these huge jumps. All right, let's talk about atomic radius. All right, in general, atomic radius is going to increase as you go down because you're adding a shell for each period. But look, it decreases as you go across. Well, it increases as you move down a column, and then it decreases as you move across from left to right. So why is that? Well, that's because they have a higher effective nuclear charge. You're adding, they're in the same energy level, which means they have the same shell, but you're adding more and more protons. So when you get more and more protons, that magnet pole on the outer electron shells pulls the radius in. So even though this only has three shells, it's got more and more protons, and those protons are pulling the outer shell electrons in, and it makes a smaller atomic radius. So this graph goes up and then curves down, so like a negative linear line. So here's period 1, and then period 2, and then period 3. Okay. All right. Now, ionic radius. How is that different? They're similar to the atomic radii, except that cations and anions are different from each other. Okay. So ionic radius is not just talking about the size and how many shells. Ionic radius is when you have a chemically neutral element, like calcium, that has 20 protons and 20 electrons. When it becomes positive, that means it lost electrons, which means it could potentially go down a shell, which means anything that becomes positive becomes smaller than its original. Okay? If it becomes negative, it gained electrons, which means it pushes out more because there's more negative and less pull from the protons. So you're going to get a not much larger, but a larger ionic radius when you're negative, right? So let's kind of give two examples. So let's do a small one. So we have lithium right here. It's in two shells. All right. So lithium, 1, 2, and it's got 2 electrons on its first shell, and it's only got 1 valence electron. If it becomes Li plus 1, that means it went down a shell, and now it's only got 2, so it actually got smaller. If I have, let's say, fluorine also is in that same thing. It's got 2 shells, 2, but it's got 7 electrons in its outer shell. 2, 4, 5, 6, and then 7. Okay. If it gains an electron, it's still going to be in the same shell. It's still got 2 shells, but it's going to push out just slightly more because that extra electron, 3, 4, 5, 6, 7, that outer shell just slightly pushes out more and becomes slightly bigger. So, oops, forgot to put the negative there, -1. So, positive cations get smaller and negative anions get larger. Okay? And that's kind of what's said here and here in the paragraph. Okay? All right. Electron affinity. So in general, electron affinity increases from left to right and decreases from top to bottom, but the arrows show the opposite. So it's the energy involved when electrons are accepted by gaseous atoms to form a negative ion. So when a neutral atom gains electrons, the values tend to be negative. That means energy is released and the electrons are added in the atoms. Okay? And then here's the trend for the graph where it kind of goes up, down, peaks, comes down, up, down, peak. So here's period 1, period 2, period 3, period 4, period 5, because you got that D group, and then it goes on to period 6. All right. And then the last periodic table trend is electronegativity, where it increases left to right, bottom to top, it decreases as you move down, increases as you move across, right? But what is electronegativity? It's the measure of the ability of an atom or group of atom to attract other electrons. And you got 3 types of electronegativity. So this is where you have 2 of the same element. The electronegativity difference is 0. Okay. Here you got polar covalent. So this is anything from, I would say this is 0 to about 0.4. This is 0.41 to about approximately 1.3-ish, 1.5-ish. That's polar covalent. And then this is typically 1.4 and plus, okay, where you get a total transfer of electrons. Right? So this is the ability of one element to steal another element's electrons. That's what electronegativity is. Okay. You need to start stating a trend is not explaining it by the arrows. Explaining trends should never be in terms of location. Because fluorine is at the very top right-hand corner, it's the most electronegative. No. Fluorine is the most electronegative because it has a much higher electronegativity value, which means it can take electrons from other elements very easily. Okay. All right, so let's do the I do and we do. It says choose the atom with the highest first ionization energy. And then all you gotta do is highlight it or circle it. Okay, so and you're doing Na or Li for A through C, and then F and O for these. Okay, so higher first ionization energy is going to be lithium. Okay, lithium is in period 2, where sodium is in period 3. For over here, because we're kind of doing this part, this side, and then this side. Okay, for between fluorine or oxygen, fluorine is going to have the highest first ionization energy because it's not going to want to give up the electrons it has. Larger atomic radius, well, sodium, it's in period 3, so it's got 3 shells versus lithium's 2. Larger atomic radius, fluorine or oxygen, well, be careful with this. They're in the same period, so they're both in period 2, but as you go across, fluorine has more protons, so it's going to be smaller. So oxygen has the larger atomic radius. Okay. Highest electronegativity. Well, lithium is going to be higher, not just because it's on top. It's higher because it's bottom to top. It's because it's got 2 periods. The protons are going to hang on to the electrons, those outer electrons, much tighter than sodium because there's more shielding in sodium than lithium. And then for fluorine's going to have the highest electronegativity because it's just 1 electron away from 8 valence electrons in its outer shell, and it wants just 1 more electron, so it's going to readily still that electron to get stable in its outer shell. All right, for the next ones, you want to rank the following from smallest to largest atomic radius and ionic radius. So remember, atomic radius is the size by shell, and the proteins play a part because they pull on the outer electrons. Ionic radius is based on if an ion gains or loses an electron. And cations get smaller if they go positive. Anions get larger because they're gaining electrons, so they push out a little bit more. Okay? So with that, if we look at the first one, sodium positive is going to lose an electron, so its shell it's going to go down in shell. It's in period 3, and it's the first element in period 3. So if it loses that outer valence electron, it's going to go down to 2 shells. So, and I'm just going to put A down here. So Na plus is going to be the smallest, where Na negative, because it gained an electron, it's going to slightly push out that outer valence shell a little bit more. So this is actually the largest. So just regular neutral Na is in the middle. Okay. All right, for B. B, we have the trend of C, N, and O, carbon, nitrogen, and oxygen, which are in the same period. So they both have, or all 3 have the same shell. Okay, so now we got to look at the number of protons. Carbon has 6 protons, nitrogen has 7, and oxygen has 8. The more protons you have, the more those protons are going to pull in those outer electron shells and make the element actually smaller. So for this one, oxygen is our smallest, then nitrogen, then carbon. Okay. C, chlorine and argon are in the same period. They're both here in period 3. But again, argon has 18 protons. So it's going to pull harder on those outer valence electrons and slightly be smaller than chlorine. And then potassium is all the way down here in period 4. So that's going to have the largest just for the sheer fact that it has another shell. So argon is the smallest, then chlorine, then potassium. And then the last one, D, beryllium, magnesium, and calcium. Well, beryllium, period 2, magnesium, period 3, and calcium, period 4. Just for the sheer fact that they have another shell makes them bigger. So it actually goes in the order that it's listed. Okay. All right. So that is your I do, we do. And based on that and the notes, you should be able to reason through questions 1 through 7. So here you just got to circle or highlight. Based on the successive ionization energies, the following element X is predict the formula when formed with chlorine. So what kind of element would this be that could form with chlorine to make these jumps? Number 3, you're looking at these two where potassium loses an electron and becomes positive. Calcium loses 2 electrons and becomes positive 2. So based on the energies, using those concepts, explain why they're different, even though the isoelectric, they have the same number of electrons that are lost. Okay. Number 4, element X has this electron configuration, where Z has this electron configuration. Based on that, which one would have the greater first ionization energy? So you're just putting X and Z for all of these. Okay. Number 5, predict 2 elements that would have properties similar to chlorine. So when we're talking about properties, you want to think family, you want to think groups. Okay. But with that, if they're in the same period, they have the same number of shells. So whatever you pick, you need to explain why you picked that element for A, B, and C. And it's 2 elements, so make sure you list 2. All right. Number 6, nitrogen in column 5A of the periodic table, which is called pnictogens. Nitrogen reacts with iodine and it forms nitrogen triiodide, which is a contact explosive that explodes with a snap and releases clouds of iodine vapor. Select another pnictogen and predict the formula and the compound that would be formed when it reacts with bromine. So something else in 5A. So 5A, one of these. Okay, so nitrogen to iodine creates a explosion. Now, what if we take bromine and match it with one of these? What would the properties be? How would it be different from Ni3? All right, based on the electron configurations, group these together, which would have similar chemical properties. So you can group them together by period or by group. If we're talking similar chemical properties, remember the alien lab from regular chemistry, families typically have the same chemical and physical properties. So you got to remember, families or groups are up and down, and periods are across. Okay? All right, so that is your topic 1.7, periodic trends. And make sure you've got your notes and use your notes to answer the questions, and I will see you in class.